we're starting the. So we talk about cosmology. So we said that the basic is the cosmological principle. Which states that the universe on a very large scale was homogeneous and we said that mathematically, this implies has a maximal number of killing vectors. And again, this is the physical. This is the physics here, right? The assumption that on a very large scale, meaning scale which is larger than even scale of clusters of galaxies, the universe is continuously isotropic. Then we did a lot of derivations, which essentially ended up giving us the general metric which obeys that, which is the Robertson-Walker metric. Squared is a minus t squared plus a squared of t times dr squared over 1 minus k r squared plus r squared theta squared plus sin squared theta d phi squared. And we said, that's the topic in space. But we know observationally that it can evolve in time. It does evolve in time. So the Robertson-Walker metric is the most general metric that describes that. It has two parameters, unknown parameters. One is AT, which is the scale factor, which multiplies all the spatial parts of the coordinates, noted at the bottom part. And the second one is K, which is a constant that we got from the, essentially from the structure of the Riemann tensor. And it can take any value, but we see that we can renormalize. We saw that we can renormalize the parameters such that if we modify the value of K, we can modify the value of the R, we can modify the value of A, such that everything is absorbed. So really, we only care about three values. Everything else can be absorbed into the scaling of the coordinates themselves. So K can be -1, 0, or +1, corresponding to open, flat, and closed universes. And when we put in these values, you need very little imagination to realize that in a flat space, this is really simply Euclidean space, flat space. Closed space, this is really a three-dimensional sphere. Don't get confused, right? It's not a ball. It's a three-dimensional sphere. It's like the surface of the Earth. The Earth is two-dimensional. So it's a surface of some four-dimensional something. Three-dimensional surface. And open is the same, but hyperbolic. Clear way of visualizing that. So I can visualize that in 2D with the sun analogy. So we have these two things, and then what we did was to plug that into Einstein's equation, but now this is not in vacuum anymore. So when we use that in Einstein's equation, use the Einstein equation, then we ended up with two equations that describe the evolution of the scale factor a dot dot over a is a minus 4 pi g over 3 rho plus b. A dot over a squared is 8 pi g over 3 rho minus k over a squared. These two equations are known as Friedmann equations. And they determine the evolution of the scale factor A, which depends on essentially three things here, right? G is just a constant. So the three things are K, the unknown parameter, rho, which is the energy density, and P, which is the pressure. Energy density and pressure of whatever there is in the universe. Then, this is essentially, we just follow exactly the same steps that we did when we derived the Schwarzschild solution. Then we did a little bit of definitions. So we define the Hubble parameter. H is defined as a dot over a. And the deceleration parameter Q is a minus a dot dot over a dot squared. Now, of course, since a, the scale factor changes in time, right? It's a function of time. Obviously, the Hubble parameter is a function of time. So today, in cosmology, today means zero. So Hubble's parameter today is known as Hubble's constant. Though again, clearly see from the definition, there is nothing constant in it. H naught is a dot over a, t equal t0. In cosmology, 0 means today. And the measured value is, we have it at 67.66 plus minus 0.42 kilometers per second per megaparsec. And then we ended up by stating that we can take the second of Friedmann's equations, which is written here, and write it down as 1 is equal to 8 pi g over 3h squared rho minus k over a squared h squared, and define the critical density called density, but it's really energy density. Rho critical, which is 3h0 h squared over 8 pi g. There's a measured value today. So rho c today is 9.21 times 10 to the minus 30 gram per centimeter cube, or 5.19 times 10 to the 3 electron volt per centimeter cube. Then we define the density parameter, omega, this is rho over rho critical, And this equation, which is the second of Friedman's equations, gets the form omega minus 1 is equal k over a squared. And that means that things are coming, now it gets quite clear why people spend so much efforts measuring Hubble's parameter. Because if rho is smaller than rho critical, the rho critical only depends, since G is very well known, the other just mathematical constants, it's just a question of what is the Hubble's constant, Hubble parameter. So when rho is smaller than rho critical, that means that omega is smaller than 1. That means that k has to be negative, because this is positive, strictly positive. So k is a minus 1, and we live in an open universe. When rho is equal to rho critical, that means that omega is exactly equal to 1, k is equal to 0, and the universe is flat. And when rho is greater than rho critical, omega is greater than 1, k must be positive, and we live in a closed universe. So in fact, there is a way of knowing which type of universe we live in. And then I told you that the surprising result is that the measured value is omega is 1.0023 plus minus 0.0055. That's the value that I have. And I want to emphasize, and I cannot emphasize it enough, right?
Isn't that K
Sorry?
instead of omega K?
It is omega. No, it's omega.
Last lecture. So,
Your last lecture. It's exactly what we said. Fully consistent with what I said last lecture. This is omega. And I'm stressing that this is a very non-trivial result. Because when you go over our entire derivative or our entire math that we did, nothing in the theory tells us what the value of omega should be. It can be anything. It could be 3,000. It can be 10 to the minus 7. It can be any value you want. It happened to be close enough to unity. In such a way that we cannot rule out any of the possibilities. So observationally, although we try very hard, we still don't know which type of universe we live in. Yes?
does most of the error comes from measuring G?
I don't think so. I think it's measuring the critical density, energy density.
G also is a pretty big error.
I think it's not such a big error. G has been known since Newton's times. There has been, so Cavendish's experiment, right? Cavendish did this experiment back in the 17th century, I think. G is from Cavendish, and of course there is error, right? G is a physical constant. So obviously there is an error, but to the best of my knowledge, G is not the main source of error in uncertainty of omega. It's more. No, I didn't get into. I may say a few more words about it in the last lecture if we have time, right? To speak about the Hubble's tension. This is something which is relatively new since the last, 10 years or so. People have realized that there are various ways of measuring the Hubble's constant, and there seems to be some tension between the different ways of measuring it. So the value that I'm quoting here, this is a value which is based on the WMAP satellite, which is kind of accepted. It is accepted. But there are other ways, and there seems to be a growing tension about that. What is the exact value? Which, of course, could change the entire physics here. So, this is the definition of the Hubble parameter. This is what we know about the universe right now. And this is a big issue. And this leads physicists or cosmologists to various ideas of how can it be that the universe will be so close to being flat. I just mentioned. Any further questions?
For the omega, we actually measure the Hubble constant.
Yeah, that's all.
And from there we get the critical value.
That's everything. That is all.
So the uncertainty that we get there is coming from the Hubble constant uncertainty.
Yes. Now we'll get there. So we'll get to Hubble's law. There's still a few more topics we need to cover before we can say that, you know, so introduction to cosmology. Or we still have 3 more lectures today and 2 more lectures. All right, more? Okay. So the next thing we're going to do is to look at, we want to solve Friedman's equations to know how the universe evolved. And he said the universe evolved, what we really mean is the scale factor, how it evolves. Now I do want you to realize one thing, right? This scale factor, this is something which is not, don't see it in everyday life. It's not something that you're used to. So the correct way of thinking of it, I'll draw it right now. What does it mean, this scale factor really? So let's say this is the time. No, this is time. And this is the coordinates that we have. Now A, this is the time, right? A of t multiplies all the spatial coordinates. Right? So if A of t evolves in time, let's say it grows with time, right? And what will happen is that as time progresses, then the distance, the real distance, not the co-moving distance, will grow. That's what it means as time goes by, right? So if you're standing here, and you're standing right here, although we're not moving with respect to each other, it's the coordinates that grow. That's what it means. I will see you receding away from me. You'll see me receding away from you. But it's not that I'm moving or you're moving. It's that the space itself changes. That's what it means. There's no analogy for that in any of the other classes you've ever taken in physics. Right? That's what it means. So have that in mind. Right? That's what it means that the coordinates are being, all the spatial coordinates are being multiplied by the scale factor.
Yeah. When I asked you last time if the observer expands with the coordinates.
The observer does not expand.
Yes, but actually it does
No.
expand, no?
The distance between objects. It's not that you grow. You're not growing.
Why not?
Right? It's not that you are growing just right and then you're growing. No, you're not. It's not that the stars are growing. They're not growing.
The distance between your eyes and your toes.
The distance between, well, here, 3 galaxies, again, there's a difference between the proper distance and the co-moving distance, right? If you're saying, okay, I'm in a coordinate r I, and this is r I plus delta r, I plus 1, if you want to take it. This doesn't change. It's just that the grid size is growing. Your size or the size of the galaxy doesn't grow. First, why not? You know why. If for nothing else, why do I tell you that the size of galaxies don't change? Because the Robertson-Walker metric is not relevant on the galactic scale. It's only relevant on the cosmological distance.
It's not relevant because of the scale, because of the,
I mean, first,
because it's small, or because it's
no. First, it's too small. Right? Even if not, I mean, this only deals with the space itself. It doesn't deal with what happens to the object in space. Okay? So there are 2 issues here, right? Is that this entire metric is relevant only on scale which is much greater than the scale of galaxies. Right? Within our solar neighborhood, of course, this is not relevant. The relevant metric is the Schwarzschild metric. Within distance, in different galaxies, this is a relevant scale. That's one thing. The other thing is that it only deals with space-time. It doesn't deal with objects on the space-time. This is a different thing. It's also kind of confusing. I didn't say anything about what happens to the object because nothing happens to the object.
So in that case, we just move to a different metric.
What?
In that case, we move to a different metric, the Schwarzschild.
We don't move, right? But this is not a proper representation of the metric in the solar nebula. We don't move anywhere, right? We're just here.
No, I don't mean move. I mean
It's
transform.
it's not relevant. This is not a relevant solution to Einstein's equation in the solar nebula. This is a relevant solution to Einstein's equation in the very large scale where this cosmological principle applies.
But doesn't it reduce to whatever we will need?
No. Because we had different underlying assumptions. Remember, when we derived the Schwarzschild metric, what did we assume? We assume vacuum. Right? When we derived that, we assumed homogeneous and isotropic space. It's not the same underlying assumptions. Yeah?
Isn't it gravitational attraction which opposes the expansion on small scale?
That's something. Yeah. Not on a small scale, large scale.
Compared to the
No. Again, don't get confused. When we derived the Robertson-Walker metric, and we derived the Schwarzschild metric, they were based on completely different underlying assumptions. Each derivation that we did was good and relevant for the assumptions that, if the assumptions hold, the metric is correct. If the assumptions do not hold, the metric is not correct. Okay? It's got nothing to do with gravitational attraction. This is, remember what we did, what were the underlying assumptions in deriving the Robertson-Walker metric. When we plug it into Einstein's equation, this metric, we ended up with Friedmann equations. It's clear? Can be confusing, but this is actually not that confusing. If you made it all the way through here, you can handle that as well. All right. Now about gravitational attraction, right? So if we want to, we're now looking at the Friedmann equations. We want to solve Friedmann equations. To solve Friedmann equations, again, we said they depend on three things. The constant K, which is, we have three options, right? We can simply solve for all three options. And the energy density and the pressure. Energy density and the pressure of whatever things there are in the universe. So in that sense, the gravitational potential will determine the scale fiber revolution. And that's on a global scale, that's not on a small scale. Okay. Any further questions? So what I want to do now, well, let's look at the content of the universe. So, remember, as part of our derivative of the Friedmann's equation, we wrote down the stress energy tensor T mu mu, so diagonal of minus rho E, right? Always part of the derivative here. So if I wrote down conservation of energy, W T mu 0 is equal to 0. I want to use that.
I have one more question. The critical value that you mentioned about the density,
Energy
includes about the energy.
Energy density.
It includes the dark energy, or
It's general. It includes everything. It's completely general. Okay. So, this is conservation of energy, right? You all see that. this one d mu to mu 0 plus gamma mu 0 t 0 plus minus. That we have a minus here. Gamma lambda mu 0 t mu. Right? That's how conservation of energy is written. Now for the gammas, remember that we derived them when we derived the orbital multimetric. That was part of the thing that we did. After we derived the orbital multimetric, we got the gammas, right? So gamma mu 0 was just a dot over a. Do you remember that? So I can write it down. So we just minus d0 rho, right? d0 t0 0, right? It's just minus t0 rho plus 3 minus right? T. Sorry, t mu 0. The other can be 0, so we don't care. Then we just have here minus 3 a dot over a. This will give me a rho, and this will give me a p. Plus p.
Isn't the lambda missing from the second term on the right hand side?
What?
Isn't there supposed to be a lambda instead of two blue zeros? Or is it just after some calculation?
You have a gamma mu. Did I miss it? No, it's okay. Just follow the rule. You take covariant derivative.
The rules say that the 0 is carried
The
once.
mu goes because everything else will give us a 0 0.
Okay, that's
I mean, here. Nu, but then if nu is different than 0, this will give me a 0. So this is equal to 0, we said. So if we want to make any progress, we need to get some relation between the energy density and the pressure. How do we call such a relation? A relation between, to make a progress, right? We need to get a relation between the energy density and the pressure. This is a question of state, right? Equation of state. Didn't even ask, I didn't. We should have started. So it turns out that all the equations relevant for us we can write down in the form P is omega times rho. Question is, what is omega? So if we write it down, P is equal to omega dot rho, then from here I have d0 rho. Essentially it will be rho dot over rho minus 3 dot over a 1 plus omega. You see it right away from here. Which is immediately integrated. So we get a rho of a proportional to a to the power minus 3 1 plus omega. Immediate solution. Okay. Yeah, rho of A is the energy density. Now the question is, okay, what do we have in the universe?
Radiation, matter, energy.
Exactly. There's nothing too much that we have really in the universe for interest. So the one is matter, and 2 is radiation. There's also what's called dark energy, but let's leave that to the side for a second. What is matter? Talk about matter. We introduced the stress energy tensor.
Like dust, stars.
Dust. Matter for me is everything that is not relativistic, like stars. And what is the pressure in stars that they exert on each other? Or dust? Dust.
Zero.
Zero, right? Has a zero pressure. So for matter, we have that P is equal to 0. Right? So if P is equal to 0, what is omega?
Zero.
P is equal to 0, omega is equal to 0. Stars don't care. Now, if the universe is dominated, and when I say we dominated universe means energetic, it is the most energetic, favorable part of the universe. And if it's dominated by that, it's called a matter-dominated universe. And for that matter-dominated universe, what do we have? Rho of A proportional to A to?
-3.
Right, straightforward. Which is very easy to understand why. Remember, as the scale factor increases, right? What happens to the gas? The density just drops down, right? And since it doesn't exert any pressure on anything, right, then just the energy density goes down. Okay. Think of this picture that I draw. Right. So if I have some dust particles here, after some time t, I still have the same number of dust particles. So now their density goes down as 1 over A cubed, right? So the energy density goes down as 1 over A cubed. It's quite straightforward. There's nothing else really. Okay, so that's number 1. This is for metric. So I have 1 and 3. The second thing is radiation. Copy that one. Oh. Now for radiation, we mean everything that is relativistic. What's the relation between the pressure and energy density for radiation? Various ways, but there is a way that I think that there is a good chance that you have seen that before. What's the relation between energy and momentum of photons? Momentum, not pressure.
Pieces of energy, momentum.
Yeah, what's the relation between energy and momentum of photon? So if I have, well now forget for a second about photon, think of molecules. So I'm putting molecules in a box. What's the pressure? I just think that you have been seeing that. Maybe you've seen that in one of your first year's terminal courses or something.
Yeah.
So if I have, well, how do I measure the pressure? What is the pressure?
The possible momentum changes when you change the volume.
It's a what?
How the possible momentum changes when you change the volume.
I'm not changing any volume here. I'm putting molecules inside this box. Not changing. What is the pressure? Other related pressure.
Energy is equal to like F divided by 2 times PV.
Okay. What is the definition of a pressure, by the way?
The change of energy in respect to volume.
Force per unit area. Isn't that? force per unit area?
Same.
Actually, it is the same thing, right? So I can look at an area here, right, and I have molecules that bounce and go back, right? Bounce and go back, right? So if I have n molecules, then the pressure would be 1/3 because I have 3 here, right? N over V and then P dot V. That's a change here. And if it's relativistic, okay, this is momentum, this is pressure. This is relativistic. So V is just C, so E is VC, so this is just C. Relativistic. So just rho energy density over 3.
Where did the third come from?
What?
Where did the third come from?
I have three surfaces here. Have you seen this derivation before?
No.
You have? Yeah. No? Something which you're supposed to see in your first year thermodynamics. Or yes.
We don't study much in thermal nowadays. Yeah.
What?
They don't teach us a lot.
I mean, they don't teach you a lot. If you completed a course in thermal, then you're supposed to see
No,
that.
we didn't complete.
You did not complete.
We didn't need that.
What?
We both doing. And they didn't have any kind of evaluation like this.
Okay. What I can recommend, I was teaching in first years of German water. You can go to my homepage, there are like all lectures that I had, and it's there. First year, an introduction to physics. It's not even term. It's basics. So you can go to my homepage, you can find it, but of course you can find it in German. It's even like the first chapter, introduction to molecular theory. It's in there. The alternative ways to do it with the Faraday tensor, but we have not introduced the Faraday tensor because of length of time, so just do it in there. Okay, so what is omega in this case? Third, right? So here we mean that omega is equal to 1/3. Okay. If omega is 1/3, what does it mean? For radiation, how does it evolve its scale factor? Huh? How does it evolve its scale factor?
A in the fourth.
Right.
Minus 4.
Right. Omega rho radiation of A will go as A to the -4. And again, this is something. So first we say that they do not evolve the same way. Right? The energy density in radiation drops down faster with the scale factor than of matter. Intuitively, you can easily understand that because now we talk about. Here we spoke about particles, right, that were just there, not moving. But now we're talking about moving particles. So it can be thought of as some sort of Doppler shift, right? Since the coordinates expand away, when A grows, you can say instantly grows, but when A grows, the coordinates expand away, and so the energy goes down. It also means something which is interesting, right? Since the energy density goes down faster, what do we have today more? Matter or radiation? Which is dominant today? Matter, right? You happen to know that, right? It's matter today. The universe is much more dominated by matter than radiation. But that means that if we go backward in time,
One point it was
What?
the radiation.
long enough in the past, when A was much smaller, this was dominating. This is of course called radiation-dominated universe. obvious reasons. This is radiation. So although today, by the way, when we speak about radiation, I said everything that is relativistic. So all the radiation comes from stars, everything goes relativistically. What is the main source of energy density, the dominant source?
thermal
Well, stars emit thermal radiation, it's obvious. I do have exploding stars, supernova there. What's the dominant term?
you ask what is the dominant energy?
Dominant energy in the radiation term.
The supernova?
No.
Black hole.
What?
Black holes.
About radiation. Black hole is not a radiation.
Cosmic microwave
Right, cosmic microwave background. We haven't spoken about it yet, but we'll get there. Right. This is called the radiation dominated universe. And this is some small exercise for first year, so if you haven't seen that, just go fill in again. All right. Today, by the way, right, what we measure today is that rho matter over rho radiation today is about 1,000, slightly more than 1,000, so about 3,000. Of course, in the past, that was not the case. Putting it in parentheses. Okay, finally, somebody mentioned properly dark energy. What?
No, no.
What?
It's 10 to the 4, no?
What happened before?
The ratio between the raw matter and raw.
No, today it's more like 10 to the 3. Slightly more. It's between 10 to the 3. It's 10 to the, it's about 3,000 and something. 10 to the 3.5. Okay. The exact value is, for me, it doesn't matter if you remember or don't remember the exact value, because we're talking about concepts. The important is to understand the concepts that there is a matter-dominated universe, there is a radiation-dominated universe. They evolve differently with the scale factor, and therefore, although the universe today is matter-dominated, there was an epoch in the past of the history of the universe that it was radiation-dominated. If you want all the details, that will be a course in cosmology, a designated course in cosmology. We'll not talk about all these details. But the concept should be understood. Okay. And what is dark energy? Now, we're not talking about dark matter. Remember, right? We had dark matter. We spoke about dark matter, which is matter. Did we speak about dark matter?
No.
No, we did not. I should. Okay, did not speak about dark matter. So let's say a word about dark matter before we move on to dark energy. Okay, so there are two things, right? One is dark matter and one is dark energy, and they are not the same things. What is dark matter? And how do we know about dark matter?
That's a kind of the matter that are racks full cavity and nothing else like some forces or
Right.
something.
So, if we're looking at the solar system, where is all of the mass that we know of in the solar system?
The sun.
It's inside the sun, right? The sun contains more than 98% of all the mass of all the planets and all the asteroids and everything that there is in the solar system. It's in the sun. And the sun, as we know, emits light. Right? So if we want to measure what is the total mass of a galaxy, for example, what is the easiest way or the most straightforward way to do that? Like there is more than one way, of course.
The nuclei.
What's nuclei?
The black the supermassive.
No, doesn't contain most of the mass of the galaxy.
Wait, what?
It's not.
Why?
Why what?
Precession.
Why not? Why,
Because
why
it does not. Have
the mass of
the black hole in the center of the Milky Way is about 4 million solar masses. There are way more than 4 million stars in the galaxy.
The precession.
What?
Precession
Precession of what?
of the stars outside the.
No.
Lensing?
Much simpler. Much simpler.
Gravitational lensing?
Guys, this is something which I believe you should have seen in an astronomy course, but maybe you haven't taken it. How do we know what is the mass of the galaxy?
Rotation.
Gravitation. What? Gravitation of what?
Galaxy.
How do you measure gravitation of galaxy?
Is Doppler shift.
Redshift.
Redshift of what?
Light.
Where?
Light.
Outside the galaxy.
And of the galaxy.
What? Guys, think. Well, that's
Redshift of neighboring arms, maybe?
of what?
Neighboring spiral arms. No?
It's
Much simpler.
Or simpler?
Go 100 years ago, right? People tried to estimate. People realized there are galaxies.
Count the stars.
That's one way. Actually, that's not too bad. Count the stars. It's not a bad. It's not a bad idea. Right? If you can. Now you can't count exactly because they get too small, right? Close by ones you can.
maybe
Very bright.
estimate the radius?
Yes, the radius of what? How can you? It's part of the question. How can you estimate the radius of the galaxy? Counting the stars is so far the best option that we've heard. Well, you count the light. You look at the light. Since very good approximation, all the mass of everything in the solar neighborhood is inside the sun, and the sun emits light. Right? And there is a way of telling, there is a way to connect how much light a star emits and what is the mass of the sun, of this star that emits the light. Right? This, you know about that? HR diagram. Okay, this is not part of this course, this is really part of course in astronomy. Life of stars, different types of stars, and how and the different spectrum that they get. And basically, bigger stars tend to be hotter, and then they emit light at different wavelengths. Right. So if you see like stars emitting all the observed and also some unobserved wavelengths, right? Big stars are emitting the bluish. There are blue stars. If you look at it very carefully, there are blue stars and red stars. Stars come in various colors. Anyway, right? So one way is simply to measure the light, right? How much? This is the simplest way, right? Measure the luminosity, how much light there is, and you get some value. You can estimate from that value what is the mass of the stars. What is the second method, which somebody said it partially? Measuring the gravitational potential. What does it mean? How do you measure the gravitational potential of the galaxy?
Lensing?
What?
Lensing.
That's it. Lensing is going to be very difficult because you need to know exactly where it is.
Look at the they some speed of us the different points from the core of the galaxy, like
Okay, and what do you measure there?
You look at the like the different times see where they are and say they don't move like this.
There are stars move around the center of the galaxy in millions of years, except those that are exactly in the center, right? Like millions of years. You won't see anything. They're not moving. That's why they call only stars that move are the planets. So what? What? Let's say this is a galaxy, right? This is our galaxy. Okay. And we're looking at the stars here. What should be their velocity? Around, actually. What would be their velocity around the center of the galaxy?
It will be determined by Kepler.
Kepler, right? It's be Keplerian velocity. Right? Now we can't see the full velocity. What can we see? We can see the Doppler boost relative to us. So we can see the component of the stars relative to the component of the velocity of the star relative to us. Right? So we know where the star is relative to the center of the galaxy. You can do it in galaxies. Whatever did it first in the 1930s didn't even do it with a galaxy. It was doing it with clusters. Clusters, in case you didn't know, right? We have a galaxy, which is a lot of stars, and around it there are like, it's called globular clusters. These are clusters of relatively much fewer stars. Can be like up to 1 million, maybe 10,000, 100,000. And there are clusters of galaxies which, again, move in Keplerian orbits somehow. The guy who was doing that first was called Fritz Zwicky. He did it in the 1930s. Very famous astronomers. I'm not sure. In the 1930s. And what did he found?
That it doesn't match.
Doesn't match. It doesn't. You'd expect that there is some errors, right? It's not supposed to be exactly the same. But how much does it match?
Very much.
What?
A lot.
By a lot. How much a lot?
Like 70% or something.
Right. A factor of 6. So there is 6 times. So the observed matter, so the matter that we see, that there is in the stars that we can see, can account for only about 15%, 1/5, of all the stars that can be of the gravitational potential that is inferred from what we'd expect from Keplerian motion. Now the one who did the most, Fitzwick was the first one, but the one who did the most rigorous and comprehensive work on that, you may have heard the name. It's a woman, she's called Vera Rubin. Actually knew her in person, she died a few years ago, unfortunately. She was making rotation curves of galaxies. Right? So rotation curves, you're looking at the faraway galaxy, somewhere in the sky, right? And you're looking at VR, V versus R's, the velocity, right? And if it's a Keplerian, so initially you're accumulating more mass, so you get the V should go up, and then it should go down. It's a Keplerian order minus 3/2, right? And what she found was that no, actually does not. As if there is some potential there that is keep on. This is called Vera Rubin. There is now a telescope that's being built named after her. She never won a Nobel Prize, so she was one of those women who should have won a Nobel Prize. For some reason, she did not. So that's Vera Rubin. It's like galaxy curves, velocity curves.
Which curve is what?
What? This is the data. This is the theory. Keplerian orbits should go, the V goes down this range. Theory and that is the data. These are the velocity curves of different galaxies. She did it for many galaxies. She looked at it was mainly in the 60s. Now, more recently, there is, you might have heard of what's called a bullet cluster. There's 2 clusters of galaxies that happen to be just moving relative to each other. And there you can do, when they move, there is a gas surrounding them, so it heats up. It heats up, it emits in 8 waves, so you can actually see it. But also, you can do gravitational lensing, which have clusters of galaxies behind them, and you can see where most of the mass is. And again, they don't match. So we know that on some large scale, there is this discrepancy. We're talking about scales of galaxies. There is still no explanation to that. one very interesting idea which was promoted by Moti Milgrom from Weizmann Institute and Bekenstein, still alive. It's called MOD, Modified Newtonian Dynamics. The idea was that we have tested Kepler's laws only on a scale of the solar system, but we don't know that they are correct in larger scales. So maybe you can add up some constant there and then to things. So that means radical change to Newton's laws. Interestingly, it was proposed in the 1970s. It has never been proven. It's likely incorrect, but it has never been completely ruled out. There are some people that are still working on that idea. It's called the modified Newtonian dynamics. Yeah.
But why do we need this when we can solve the full GR wave?
GR doesn't tell you what's in there. I
No,
just
no,
explained what is the dark matter. GR doesn't tell you anything about the dark matter.
I mean, why do we need to model if I have a close for large scales when we have GR?
Well, on a large scale, we saw that. On a large scale, GR would coincide with the Newtonian physics, right? When we have Schwarzschild solution, right? If you go very far away,
Yes,
right,
but
and
still
GR gives you exactly Kepler's laws. Correction is going to get smaller and smaller. So you cannot explain that with some modified metric. I mean, maybe you can. Nobody found solution. Okay, so this is dark matter. So dark matter is matter that we know it's there because it attracts gravitationally, so it does apply gravitational potential on other matter that is there, but is not seen. There were, over the years, there are various ways, that's called particle physics, which are called WIMPs, weakly interacting massive particles. They thought that maybe there are like small black holes that are surrounded somewhere in the galaxy that we don't see them because they are black holes. They were all ruled out. There are various experiments trying to detect, in particle physics, trying to detect various such particles which will go beyond the standard model particles. And so far there is no firm detection. That makes, and by now people have done that for many years. So at least for 40, 50 years people are searching for it. Haven't found anything conclusive yet, so now people start to think maybe we're looking at the wrong regime. But of course it's very difficult to say if you have it, if you don't have it, you don't see it. Alright, it's okay. It was a little bit of detour about dark matter. So what is dark energy? So this was dark matter, right? So matter is matter that attracts gravitationally, but does not, we don't see it. That's why it's called dark. While we would expect it to see as same as the sun, lights, shines light. What is dark energy?
Dark energy relates to the expansion of the universe.
Right. So what do we mean the expansion of the universe?
So basically,
now we're going back to GR. Right? What is this dark energy thing? What did we say? We plug in Einstein's equation.
Acceleration.
No, we're going back. Forget about acceleration for a second. We haven't spoken anything about the evolution of things. What did we have in Einstein's equation?
the lambda.
A lambda term, right? So remember that in Einstein's equation, now we're talking about dark energy. So in Einstein's equation, right, and G mu nu equal 8 pi G T mu nu. Right? Then we said we can add up the cosmological constant minus lambda G mu nu. This is the cosmological constant. Remember, Einstein initially added that because he wanted to keep the universe steady. That's what he thought. That's what he believed. only a few years later, Hubble showed the universe is not stable. Okay. What about this term, lambda G mu? Think of it now, we can write it down instead of minus lambda G mu nu. Right, we could simply write it down. T mu nu vacuum, right, minus lambda over 8 pi G, G mu nu. And we end up that Einstein's equation will be written as G mu nu is 8 pi G, T mu nu plus T mu nu vacuum. The same equation, it's just a different interpretation. Right? So now let's forget about this term. Let's just assume that we have this term. So T mu nu vacuum is a minus, so G mu nu is a minus lambda G mu. So if this is T mu nu vacuum, what does it mean about the relation between rho and P?
Won't P be 0?
What?
Minus 1.
This is T mu nu there.
Oh wait, T mu nu and T vacuum?
Yeah, let's assume that there is no T mu nu here, right? But just T mu nu vacuum. Right? Let's say that I can neglect this part. This is the dominant part. What would be the form of the equation of state? That's what I'm looking for.
Oh, the equation of state, okay.
Right? So we have minus 1, right? Because G mu nu is a minus 1. Right? And then it will be a plus. About that, right? Just a plus, right? So we have a minus and a plus, right? So that means that the equation of state we're going to have
Negative.
rho is equal to
Minus 1.
minus P, which is simply lambda over 8 pi G. So what is omega?
Minus 1.
Omega is a minus 1. And then the rho lambda proportional to what?
I to minus 4.
I don't think so.
To 0.
A to the power 0. Right? Now that is strange. You have never encountered anything that looks like that in any of your physics classes. Right? What does it mean?
The energy density is constant.
Well, not necessarily. It is independent on A, scale factor. Right? Which means that what? The more, remember, right, this T goes by, the more our coordinates increase.
Doesn't change.
No, it does change. What happens?
Then at the A goes.
What?
Closer.
We have more vacuum.
Expense with it.
Have more vacuum.
We
We
get
have
more energy.
more energy. Energy is created out of nothing, right? The more vacuum we have, the more energy there is. That's called the vacuum energy, right? Or the dark energy. Again, it's got nothing to do with dark matter. Right? Dark matter is a matter that we know is there. We just can't. We know it's there because we can see its gravitational attraction. This is an energy that is associated with the vacuum in between intergalactic space. And the more vacuum we have, the more energy we have. So this would cause the universe not only to expand, but to accelerate. Now again, the accelerated expansion, right? Again, there is no physical intuition, right? In the everyday life. It's nothing like you've seen before. Okay. Normally, when you're increasing the pressure, right? You used to think of it, okay, I'm increasing the pressure of something, I have more energy inside, the energy density increases. This is the opposite. I'm increasing the pressure, I have less energy. Yeah.
Yeah, this is what I was asking about last week about, doesn't this mean that there's something putting energy into the system? Like,
Yeah.
what's going on?
Good question. What's going on? What's going on is that yes, the more vacuum we have, the more energy it contains. Yeah, so there is something that we don't understand that puts energy into the system. Remember, I told you in quantum field theory, even if you study that, the effect of Casimir effect, which shows that there is vacuum energy, but the values are completely different than what we have here observation. This is something which we can observe, so we do observe. Do you happen to know what's the rough values today?
I used to, I forgot.
For row, what's row?
70%.
It's like yeah,
70%, right? So rho, so today, rho vacuum is about 70%. Rho matter,
30%.
right, 30%, but out of that, we said about
Dark matter.
about 25% of that is dark matter, which we don't see. Something like 25% dark matter, and 5% is what we see.
Very honest.
That's the stars, right? This is what we see. So this is the universe we understand. This 5%. This contains that's regular matter. And radiation.
It's like 10 to the minus 5, so
It is no, it's more than 10 to the minus 5. By the way, it's called colder.
0.01.
It's negligible. Yeah, it's actually it's something like 10 minus 3 ish. 10 minus 3, 10 minus 4. I'll give you the exact numbers right here. I have it written. So this is negligible. This is actually called cold dark. I should say CDM because it's cold dark matter. I don't know if I have time to say a few words about it. So you've seen this picture saying, okay, 95% of the universe we don't understand. That's where it comes from. This is the 95% we don't understand. Out of the 70% is the vacuum energy. 25% is the cold dark matter. Yeah.
Why do you need to look at this as a vacuum energy and T vacuum instead of just the cosmological constant as another solution to Einstein's equation?
Cosmological constant is not a solution to Einstein's equation. It's part of the
It's
equation itself.
another option for the.
It's not another option. It's part of the equation.
Yeah.
It's in there. Remember, it is consistent. Adding that term is consistent. This was the original Einstein's equation. Adding this term, initially Einstein did because he could not find a solution that will keep the universe steady. Hubble showed the universe is expanding through a sort of way. This has been reintroduced back in 1998 or 1999, so 70 years after Hubble's initial discovery, right? When people have realized that the universe is not just expanding but is accelerating. This is a work by Adam Rees and Saul Perlmutter using Hubble Space Telescope. Okay? But this is still the equation. Now, I said that when we discuss this equation, you can put this term here, then it gets this part is the matter, right? This is the physics here, and this is the geometry. You can take this term, put it in the right-hand side, this is a physical part. Then it's an interpretation. Then the interpretation is of, this is the interpretation. That there is dark energy. If you want, you can put it here, but then it has a geometrical meaning.
Yeah,
Right.
that's what I
This is not a solution. This is just the equation.
Yeah.
We're trying to solve it. Right? Fine? Can we move on?
Basically, we
Yeah.
actually realized that this the acceleration occurs when we started to measure very distant galaxies.
We'll get to Hubble's. We're not there yet. Have to wait another. Well, we still have 2 more lectures. We'll get there. Okay. course, the measurement is of how. Get it. I promise you, we won't finish this semester before talking about atoms. Right? Okay. I know it's exciting. That's the way it is right now. So this is the current state. But of course, have in mind, right? All of these one of three ingredients have a different dependence on A. So that means that when A was, so today we are vacuum dominated. But only recently it happens. If you go back in time, not too long ago in cosmological terms, it was the matter dominated, right? If you go further backward in time, at a certain point it was radiation dominated. So the universe has changed in terms of what's the content of the most. All right? Yeah.
One more question. There is an estimate that for each matter there is
Great.
each matter element there is 10,000 photons. This estimate came from for the estimation of the annihilation.
We're talking about different things.
Okay.
Right. I said that for radiation, the most important is the dominant contribution is from the cosmic microwave background. And you know what is the density of photons in the cosmic microwave background? This is something which is measured. You know what is the temperature? You know what's the black body? You know what is the density of photons per centimeter? It's about 500 photons per centimeter cubed or something like that. And you know what is the density of gas? Okay, there are various ways to estimate. All right, guys. Can we move on? So now, I think I can erase it. Can I erase that? Maybe I should erase. Maybe I should stick with that because we need that. That's the basic, and let's move on to talk about that. So we finally were in a position to, or maybe let me rewrite it again. Raw matter goes to the 3, raw radiation goes to the 4, raw vacuum goes to the 0. So in principle, now we have everything we need to solve Friedman equations. Right? But of course, we can do it. It's a bit tedious. So we can look at the different possibilities and explore what happens in different possibilities. So for now, for the sake of discussion, let's assume that there is no cosmological constant. So assume lambda equal to 0. So no cosmological constant. Most of the time we could. And let's say that the universe has something which has a positive energy. Rho greater than 0. And non-negative pressure. P is greater or equal than 0, which makes sense for now. So from here, in this Friedman equation, what do we have? This has to be positive, this is non-negative, which means that A dot over A needs to be negative, right? So that means that A dot over A needs to be negative. Which simply means that A dot is negative. This is simply from the first of Friedman's equation. Now I don't need to tell you, right? Hubble tells you that the galaxies are receding away from us, which means that A dot is greater than 0. We know that A dot is greater than 0. The universe expands today. Which means that if we are plotting T, this is A of T. And this is today. Right? So A dot is greater than 0 today, but A dot dot is smaller than 0, so that means that in reality what we have is that A of T should do something like that. Some sort of a concave shape. And of course we can take it back. So physically what happens here, right? A dot is A is increasing, right? A dot is greater than 0, so means that A is increasing, so the universe expands. But A dot dot is smaller than 0, so the expansion slows down. Right? And then again comes the physical intuition. Why is the universe slowing down? Why is the expansion slowing down?
Gravitation.
Right. That's the only thing that there is, right? Because there is something in the universe which attracts everything else. Right? So because of this attraction, you had started with something, right? And then it stops. Right? So whatever in the universe is slowing it down. Of course, if you're going back, let's say, for example, just for the sake of argument that A dot dot was exactly 0. Right? If A dot dot was exactly 0, then we can trace back in time. How would it look like? If we're tracing back in time, just be a straight line. And what will be the distance? What is that?
The age of the universe.
Of course, it's which is equal to what?
14 billion.
What?
14 billion years, 13.
13.8. The age of
From the equation that we saw today, what this is equal to?
Hubble.
Right. 1 over Hubble, right? Hubble is A dot over A. This is simply 1 over H. Minus. 1 over the Hubble really tells us what is the age of the universe. Of course, since A dot dot is not 0, but is smaller than 0, that means that the actual age of the universe must have been smaller than 1 over the Hubble. Of course, this is A is equal to 0. So how do we call this point where A was equal to 0?
Big Bang.
What?
Big Bang.
Big Bang. This is the Big Bang. A equal to 0, so this is here. This is the Big Bang. Now some misconceptions. Okay, there are various misconceptions that you find in various textbooks, so I just won't even go over all of them. Here is the right way of thinking of it. The universe does not expand into anything. So for A equals 0, the universe expands into not anything. The correct way to think of it. Are you still using like Xerox machine to copy things, or you don't do it anymore? Not really, but you know what a Xerox machine, right? When I was a student, we used to do it all the time to copy from books, to copy from each other's notes, right? You know what are these machines?
Scanners.
Scanners, right?
How do you
Hold
call
on. Xerox machine. Photocopy.
מכונת צילום.
מכונת צילום. Make a photocopy. Right? You know what I'm talking about? They have one in the secondary. Right? You know. Now you know that in these photocopying machines you can do a zoom. know that you can do zoom in, zoom out? You ever think of that? So my generation is changing. When we wanted to make copies, we had to take each other's notes, and then you can do like a 50%, and you have this like small, like you know that, right? You can do, you have all the data that there is in there, and you can simply photocopy, put the paper, and you can photocopy, and you can make it smaller or bigger, right? So think of a Xerox machine. You have some data, right? And you're photocopying it, but you do like a 50%, right? Then in principle, you're not losing any data. It's just everything is much smaller. That's what it means, right? The scale factor goes down. Now you can do it again, right? You can take like the new thing which is smaller. You're with me? You understand what I'm talking about? Take a piece of paper, write something in it, and then make a photocopy of that and do like a 50% shrink. You're not losing anything, just the paper that you had would now be like that. And everything which would be in it, right? You still have it, but it's going to be smaller. More difficult to read, but more condensed. Right? Fine. You can do it again. Do it again to get something which is even smaller. Still didn't lose anything. Now, of course, at a certain point, you reach the technical limits of the machine, right? So you will lose information because the machine cannot do smaller than that. But this is the universe, so we don't have it, right? So you can still keep on going and you don't lose anything. Another thing, of course, the machine can only take papers of finite size. But let's say that the machine, imagine a machine that can do a paper of infinite size. You shrink it into two. Everything is condensed into two. What is the size of the new paper? What is the size of the new paper?
If everything is condensed into what?
Well, I take a paper of infinite size and I condense it and put a 50%, so everything is condensed into two. Infinite, right? Because infinity divided by 2 is still infinity. And you keep on doing the same, so you squeeze it into 2 again. What's the size of the paper? Infinity, right? So that is the Big Bang. You're taking everything in the universe, you squeeze it, you squeeze it, you squeeze it, it goes to 0. But what is the size of the universe? It's still infinite. Just everything is closed by, right? That is the meaning of the scale factor going to 0. If the universe was infinite, is infinite, but let's say it's flat, right? You can do the visualization by yourself, if it's closed or open. But if you're taking this universe as infinite, if it's flat, it was still flat. It was just infinitesimally dense. Of course, at a certain point, when it gets too dense, the known laws of physics fail, right? Because we can know as much as we can. Right? That's why when they do in CERN, they go to higher and higher energies. What they really do is they're going to more dense and dense energy densities, which means that they go backward and backward in time. So they can study what were the conditions in the very early universe. You might have seen there in some textbooks, like first 5 minutes and things like that. Hopefully we could finish this semester talking about it. But that's what really happens here. So when we speak about the Big Bang, it is not that the universe, has some finite size and exploded into void. It was infinite. If it is infinite today, it was infinite back then. It was just infinitely condensed. That's what it means. This is some point that most textbooks somehow miss. Right? That's what it means. I think this is a much better analogy than what you find normally. Right? So this is the Big Bang. A was equal to 0, and it's limited, right? It's smaller than 1 over h0, and you're right, it's something like 13.7 billion years ago. So again, this is the Big Bang really represents the creation of the universe from a singular state, if you want. But this is not the expansion of matter into another pre-existing state universe. Right? That's the first conceptual thing that is important to look at. All right. One more thing is that we get it. You don't need to have the universe to be perfectly symmetric. You can get the same behavior if the universe was not perfectly symmetric. You get some of different equations. thing is that, of course, once A gets very small, the energy density gets very large, and at a certain point, the known laws of physics fail, so we cannot really tell what goes on. Simply because nobody has ever tested it experimentally, and remember what I told you in lecture number 1. Physics is an experimentally based science. So that is the past, the Big Bang. What is the future? What's going to happen in the future?
It's gonna continue blowing up, no?
What?
It's gonna be constant.
Do you have any other alternative?
Maybe it shrinks.
Maybe it shrinks back, right? You have 3 options, right? It can continue to go up, it can be constant, and it can go down. It can go down back again, right? So actually we can calculate that. Don't need to assume anything. We have all the tools we need to calculate what would be the future evolution of the universe. So let's do that. We don't need that more. So let's do that. So it turns out that the future evolution depends on k, values of k. So for open and flat cases, open and flat. What is k for open and flat?
For open and
flat.
-1.
Minus 1, right? So we know that k is smaller or equal to 0. Then we can write down the second of Friedman's equation, a dot squared is 8 pi g over 3 rho a squared plus absolute value of k. Now, if rho is greater than 0, that means that everything here is strictly positive. Everything here is positive, which means what? This is positive, that means that a dot is always greater than 0. Never passes through 0. Why?
Why did you do the absolute of k?
Because k is negative. Or minus k. So what?
But A dot could be negative.
What's the problem?
Square.
What?
Minus and minus.
Well, what's the problem?
Square.
Yeah, it means that a dot is. The only thing I want to say is that a dot is positive at all times.
But it's necessary.
Okay, so what? But a dot today is positive, and a dot is positive at all times. Because a dot today is positive. A dot today is greater than 0, which means it has to be positive at all times. It never goes through 0. Okay. So, what do we get from here? What's the conclusion?
Doesn't collapse.
We always expand.
Always. So, the conclusion is that open, flat, versus expand forward. Cool. You want me to take you another 10 minutes and actually derive it, or you want to do it for next? Let's finish that if we start. So that means that it's going to expand forever. Now we can calculate how much. It's not too difficult. So again, let's assume a metric-dominated universe. It's just for easiest of comparison. So we've written the energy conservation equation. So let me write it down again. It's right. Energy conservation. Right. 0 is blah mu t mu 0, which is minus rho plus minus 3 a dot over a rho plus b. Now it's a matter of straightforward algebra to see that what is really written here is d over dt rho a cube is a minus 3a squared a dot b. I didn't make any assumption about the method of manipulating universe. Just plug it in here and you'll see. I just multiply by a squared, and then you'll see that these two terms go to the left hand side, and that's what you get. Right. That's straightforward. Now, since a dot is greater than 0 at all times, p we said is positive and non-negative, which means that d over dt of rho a cube must be smaller or equal to 0. So if a goes to infinity, since this is negative, what does it mean? What can we say about rho a squared? No. The over the t of that is more than 0. Right? When a goes to infinity, if I know that the derivative here is negative, what does it mean? It must go to, yeah. Okay. D over the t of rho a cube is negative. So if a goes to infinity, right, this is d over the t of rho a squared times a. When a goes to infinity and the derivative is negative, what do we mean about rho a squared? Has to go to
negative infinity?
Cannot. To 0. Think about it a little bit.
Smaller or equal to the 0 means it can be minus infinity.
What? No, if a goes to infinity, the rho a squared needs to go to 0.
The equation on the left,
This is just saying that d over the t of a cube is smaller or equal than 0.
it could just be that rho a squared is negative.
Rho is positive and a squared is a squared, so it has to be positive. Okay, think of it a little bit, guys. So from here, if rho a squared goes to 0, when a goes to infinity, rho a squared goes to 0. That means that a dot squared goes to k. So a dot squared goes to k when a goes to infinity. Again, this is only true for k, which is 0 minus 1, right? Open or flat universes. Okay. So we know what are the expansion, right? So the expansion now will approach. If it's a flat universe, a dot will go to 0. So that will approach some sort of finite, right? A dot goes to 0. And if it's minus 1, then a dot is going as 1. So something like, I don't have it here. Essentially, it will look very simple. Just a dot goes to 1. fact, essentially you can write down this A of t equals t to some parallel. A of t equals t to some parallel alpha or alpha equals 0. Give you that. That's fine. All right. That's for the open flat universes. No cosmological constant, so no vacuum energy. In some sense, it does not represent what we have. Okay, now closed case will speak on Thursday. All right. Questions? Look, guys, I don't consider this to be a very difficult part of the course, especially relative to the other things we're going through this semester. We still have 2 more meetings on Thursday and then next week on Sunday. And there is still, we haven't finished, right? There's still plenty of material to go through. I strongly urge you, if you find these things confusing, now is the time to go and make sure that things are clear in your head. Right? Okay, have a good week and see you on Thursday.
דבר נוסף,